let's take a look at another example. So in this example, we're considering the system shown below, and we want to find several things. We want to find the system type, the appropriate error constant, and the steady state error, all for a unit step input. So because we're told that we want to find the steady state error, we're going to assume that our input and output have the same units. So assume R of S and C of S have the same units. Now, if our problem statement had asked us to find the steady state error in the actuating signal, then we would need to assume that our input and output had different units, and our approach to solving the problem would be slightly different. But in this case, we're assuming that they have the same units. So remember, something that we've sort of been glossing over as we work through these examples is our very first step, if we were actually working this, is we would need to check for system stability. So need to check stability. And so that's something that you could do as extra practice, and if you have questions or issues as you're doing that, definitely let me know. But because we're focusing on our steady state error in this unit, we're going to go ahead and assume that our system is stable, and we're going to move on to our next part. Now, because we don't have unity feedback, we're going to need to use our updated expression from a couple of videos ago, where we said, how do we find all these things for a non-unity feedback system in the case that we have the same units for our input and output. And in that video, we came up with an expression for an equivalent GEQ that was equal to our G in the numerator divided by 1 plus G times H minus G. And so all we need to do is plug into that equation, and in this case, what we're using for G is this 100 over S times the quantity of S plus 10. And we're using for H that feedback block, which is 1 over S plus 5. And so if we plug in and do some algebra, we can find that the GEQ ends up being 100 times the quantity S plus 5 in the numerator divided by S cubed plus 15S squared minus 50S minus 400. And so again, that's another good place to sort of get some practice. If you want to practice with the algebra and plugging in, I encourage you to do that. And if you run into issues, let me know if you have those or other questions. Okay, so now that we have our GEQ, remember what this is now we have some system that has a GEQ block. We have our summing junction here. So we say we have our C of S. And now this is for a unity feedback system. So this represents a system that looks like this. And so what that means is now we do have some error signal here, and we can go back and we can use all those techniques we talked about before when we were looking at unity feedback systems. We just have to use this GEQ. So if we do that, now we're considering this GEQ. The first question was, what is our system type? So for our system type, remember we were looking at sort of the general expression of G. So we said G can be written generally as S. So we had some gain factor S plus Z1 times S plus Z2, so on and so forth. And in the denominator, we had S to the N times S plus P1 times S plus P2, so on and so forth. And we said our system type is equal to the number of this N variable here. So in this particular case, we're looking at this denominator. We notice it's not in factored form, so that can make it a little bit more difficult to see. But it's a little easy if we think about it, because we see with this negative 400 term, that means that we can't factor out an S from all of our other terms. So because we can't factor out an S from that denominator, we're going to say that our system type is 0. So type 0, or in other words, the N is 0. Okay, so because we now know our system type, that gives us a little more guidance in terms of what is our appropriate error constant. So thinking back to the table we saw previously, for a type 0 system, our kV and our Ka, our velocity and acceleration constants respectively, were both infinite. Rather they were 0, meaning that we had an infinite error. So that means we're going to be focusing on our position constant. So if we're looking at our position constant, so let's just say type 0 means we're focusing on our Kp. And so remember, our Kp is equal to the limit as s goes to 0 of GEQ of s. And so really it's just g, but I've put in our GEQ because that's sort of what we're replacing our g with. And so if we come up here to our general g expression, we let our s's go to 0. So all of those terms with highlighting are going to go away, and we're just going to be left with 100 times 5 in the numerator. So we have 100 times 5, and in the denominator we just have the negative 400. And so that gives us negative 5/4 for our position constant. So this is our static error constant, K sub p. So remember, and now our last thing is we want to know our we want to know our steady state error. And so all of this again is for unit step input. So, and that makes sense because remember our Kp for type 0 corresponds to a unit step input. And so if we want the steady state error based on all of these things, it's really simple. Once we already have that static error constant, we can say our steady state error is just 1 over 1 plus Kp. Plugging in that value, we get negative 4. And so one thing to note, we've not seen a negative steady state error before. So all that negative value indicates is that our output is going to be larger than our input in sort of our steady state as t is going to infinity. So output larger than input as t is going to infinity.